Okay, guys, here's the first example we're going to do. It's just a beam with concentrated load simply supported on either end. Through some of the forces, some of the moments, these reactions are calculated on an exam or on your homework. You're going to be expected to be able to calculate what those reactions are. Here's the tip. If your beam is not in static equilibrium, don't even bother doing what we're about to do. It's not going to work out. So as if anything, just like in the method of sections, method of joints, all those slick ways to calculate what's going on in a beam, if you're not in static equilibrium to start, you're just going to get junk. And it's very frustrating. This is a pretty long problem, as all these are. And if you don't get them to close out, as we'll say, it's going to be mainly because you don't have static equilibrium. So anyway, here's the reactions: RA 5.98 kilonewtons and RF 5.8 kilonewtons. So what we're going to do, we're just going to do the shear force pretty fast. All right, I'm going to show you exactly what I'm going to do. So I'm going to start at 0. So you're going to put a shear force line and a moment line, hence a shear moment diagram. You can always start at 0. Make sure you put the V and the M, and you put the units there, kilonewtons. This is going to be kilonewton meters, despite that we're working. I'm sorry, and these is 400. These are in millimeters. 400 millimeters, 400 millimeters. This is 300 and 300. Sorry. 300 millimeters. Okay, so we're going to do the term, the bending moment in Newton meters, kilonewton meters, because of the decimal points, and we don't want them that large. So what I'm going to do is I'm just going to do the shear. So right here at 0, I'm going to go up 5.98 kilonewtons. I'm going to draw a line, right? That's going to be, and then constant in between, the shear force between two concentrated loads is constant at 0. So then we're going to go straight across here to B, right? So this is going to be 5.98 because that's how high this went up. And then at B, I'm going to go down 3.5 kilonewtons, right, which is not all the way, to right there, right? And then I'm constant again here. And this value here is 5.98 minus 3.5. That's going to be 2.48, right? And at 2.48, I'm going to go down another 4.3 kilonewtons, right? And that number is going to be minus 1.82. I'm going to go straight across again. I'm at negative 1.82. I'm going to go up 1.2 kilonewtons. I'm sorry, I'm going to go down again because the arrow is going to go down. So I'm right here at 1.82, and then I'm going to be constant across a concentrated load with no load in the middle, and then I'm going to go down another 1.2 kilonewtons. So 1.2 plus a minus 1.82 is a negative 3.02. Sorry, 3.02. Then I'm constant again, so I get to E, and at E, I'm going to go down another 2.8 kilonewtons. I'm going to go here. So 2.8 kilonewtons added to negative 3.02 kilonewtons is 5.82 kilonewtons, negative. I'm going to go here, and you'll see at my reaction, I'm going to go up my 5.82 kilonewtons, and it's going to close up at 0, okay? And basically what we want to do is we want to shade everything between the curves and the x-axis. Okay, so once again, I start at 0, I'm going to go up 5.8 kilonewtons. I'm constant in between the two loads. I go here, I go down 3.5 to 2.48. I go constant. I go down 4.3 to 1.82. Okay, I'm constant. Go down another 1.2 to 3.02, constant. Go down another 2.8 kilonewtons to 5.82, come across, close up. If this curve does not, if this chart does not close up at 0, then you've done something wrong, right? The shear force is pretty easy to do, okay? And what I was saying is the shear force is constant between the concentrated loads. So meaning if I took a cross section here, if I cut the beam right there and looked at it, the shear force would be minus 1.82 kilonewtons. So that's easy. The shear part of it's pretty easy. Now, the moment chart is a little harder to do, right? So basically, this is the integration part of it, meaning on every part of the moment curve, any point along this curve, wherever it's going to be, is the actual area of the shear curve above it, okay? So for the moment curve, I'm actually going to use this section over here to generate it. So I did this real fast because I can, okay? But I'm actually going to break down each point one at a time. So at point A, I'm going to go here. What do I know? I know that VA is equal to 5.98, sorry, 5.98 kilonewtons. That's my value, my shear value at A. That's A, 5.98. A simply supported beam, the moment always starts out at 0. So my MA is equal to 0, right? We're going to start right there. The only time that the moment does not start at 0 is for a cantilever beam, okay? We're going to do a cantilever beam example or two in the course, but every other time, moment values always start at 0. Okay, so at point B, that's going on here, right? So at point B, my shear at B is going to be my old shear, which is going to be 5.98, right? And I'm going to go down another 3.5, and that gives me 2.48 kilonewtons. And that's basically what I just did here, right? So that's at B. What I drew is now done mathematically, okay? Now, the moment at B, here's where the tricky part comes in. The moment at B is my old moment, which is moment at A, which is 0, right? And we're going to say plus the area of AB. The plus sign it's plus because this area here, AB, A to B, is above the x-axis, right? It's above the horizontal axis. If this area were below, that would be a minus, okay? So the MB is MA plus AB. This is going to be equal to 0, right? And AB is what? Area AB is 5.98, right? This width, what's the height? I'm sorry, no, the height is 5.98. What's the width? 400 millimeters, right? So 400 millimeters times 4.98. So we get 5.98 times, let's say 0.4 meters. Okay, and we get a value of 2.392 kilonewton meters. Okay, so we're going to start at 0. Now that's our second point on the moment curve. So we start at 0. And we're going to go a straight line from here to here. And this value here is going to be 2.392, okay? We go a straight line because we're going to increase the order of the curve. This curve we said earlier, this is going to be a horizontal line. That's going to be a 0 order curve, right? 0 order curve is a horizontal line. As we go down in charts from shear to moment to slope to displacement, we're going to increase the order of the curve. So we start at 0 order. The next curve we write going down this way is a first order curve. A first order curve, we said, is a straight line. So we go straight line from here to there, okay? So now we're going to go to point C, okay? VC, the shear at C, is equal to my old shear, which was 2.48, right? And we're going to go down another 4.3. And that's equal to minus 1.82 kilonewtons. We already have that on the chart, no problem. Now, my MC, moment at C, is equal to my old moment, MB. Now, this area is still above the curve, this area right here, so it's going to be plus, right? And that's going to be area BC, okay? That's basically equal to, what's my MB number? 2.392. And area BC is going to be equal to 2.48, right, times 400 millimeters, or 0.4 meters. Okay, and for that, we get a value of 3.384 kilonewton meters. That's my next point. This is 2.392. We better be here. We're going to go up a little higher, and we're going to go a straight line there. Okay? And how you draw it to scale isn't that important. It's just important that you do draw a straight line, 3.384. That's that value right there. Okay? Okay? 0 order curve, first order curve, okay? At point D, what's going on at point D? VD, shear at D, is equal to my old value, VC, which is minus 1.82, right? And here we're gonna say minus 1.2 because now the area here between C and D is below this horizontal axis. That's why this is a minus, okay? So that's gonna be equal to minus 3.02 kilonewtons. And we've already got that there. You see that right there? We're just doing it mathematically, but we can start the problem just by doing it quickly. That's a good way to do it, to see if your curve closes out and to continue. If you don't close out doing it quick, you know you got something wrong with your reactions. Now, my moment at D, which is going to be right here, is equal to my old moment, MC, right? And here, once again, the area is below the curve, right? Oh, I'm sorry, I misspoke. So with VD, this minus sign is simply because this vector is going down. That's why it's minus. Here's where the area comes in. So the area between C and D is negative. It's below the axis. So this is going to be MC minus area CD. And MC is going to be equal to 3.384. And area CD is what? Minus 1.82, right? And its width is 0.4 meters. So my MD value is equal to 2.656 kilonewton meters. So I've gone down, right? I was at 3.34. Once again, zero order curve. I'm gonna go linearly to a straight line down to a value of 2.656. I'm gonna go straight down here, okay? We get to point E. My shear value at E is equal to my old shear value, VD, plus the load at E, which is going to be, or minus, 2.8 kilonewtons. Let me just write off the numbers. It's easier without doing all that. So VE is equal to negative 3.02 minus 2.8, and that's equal to negative 5.82 kilonewtons. Already shown on the graph, that's right there, right? My ME, moment at E, is equal to my old moment at D, right? This area is below the curve, this area between D and E, so that's gonna be a minus, okay? MD minus area DE, and ME is going to be equal to, the value MD was 2.656 minus area DE, which is 3.02, and this is 300 millimeters wide, so 0.3 meters, and we're going to get a value at E of 1.75 kilonewton meters. 2.656, I'm going to go down to 1.75. Once again, zero order curve, straight line there, okay? Last point, point F, VF, is equal to my old shear value, which was VE, which is minus 5.82, right? And I'm gonna go up now, plus 5.82, right? And I better get zero, so that's true, that closes up the curve. My MF is equal to my old moment, ME, right? Once again, this value, this area is below the axis, so that's going to be minus area EF. And let me move up a little bit. My MF value is equal to ME, which was 1.75, and area EF is equal to here's the total area, right? This is going to be 5.82 times 300, or 0.3 meters, and that's going to turn out to be 0. So the moment has to start and end at 0. Now, once we have that curve, we're going to fill in all the space beneath it. So here's the whole point of doing this exercise. If we wanted to calculate sigma is equal to MC over I for this beam as loaded, where is the moment, the highest moment, and where does it occur? Well, obviously it occurs at point C. So the value you would plug in here at M, you would plug in a value of 3.384 kilonewton meters, right? And it occurs at point C. That's the whole point to do this, figuring out on this complex beam where it's loaded like that and the number. So that's the whole point. Now, I could ask you, if I gave you the cross section of the beam, if it was an I-beam and you knew the geometry of it, what's the stress at that point? You could just calculate C and I, and you can give me the bending stress right there. In fact, with this equation, you can give me the bending stress anywhere in the equation, because everywhere along it, we know the moment values, right? Now here's to reinforce the point we did. This point here, this 2.392 is equal to the area before it. This 3.384 is equal to the sum of the area here. This 2.656 is equal to the sum of all the areas there. So hence, once again, the calculus aspect of it. Any point on this curve is equal to the area underneath the curve of the shear. And if we did the next curve down, which would be slope, every point on that slope curve would be equal to the area of the moment curve before it. Okay, this is one example. We're going to do 5 total, and hopefully it gets a little clearer. Okay.